Hi. How's everyone doing today? Cold? A little bit? Just a quick question. Who here is like doing computer science or taking some kind of software development classes? Just, okay. Basically everybody. All right. Awesome. And who here has seen the Karpathy talk or read the original Medium article where he describes Software 2.0? Has anyone seen that or read that? No? Oh, awesome. So just to give him the credit for the name, Software 2.0 is a term that was coined by Andrej Karpathy. He's the director of AI at Tesla. And he kind of identified this trend that many of us in the industry have started to see. This trend is coming about because of the advancements in the capabilities of machine learning and kind of the recent successes that we've seen with deep neural networks and some of the AI breakthroughs. So my goal here is not to talk too much about specifics of machine learning, but it is to kind of convince you that there's this revolution that's happening in the software development process itself because of it. However, before we talk about that, just mention that I'll be teaching as an adjunct next quarter here in the spring, doing big data. So if that sounds interesting, you want to learn about what is big data, why does it matter, and how do engineers in the industry kind of approach these problems of, that come about with data at scale, I highly encourage you to enroll. It'd be super fun. Just about myself, this is a picture of my wife and I in Hawaii. We like to travel in particular places that have more sunshine than maybe Seattle does. I'm a software engineer at Microsoft. I've been there for a couple of years now. I work on a big data analytics team that's responsible for Windows and Azure reliability. So we basically make sure that the operating system and kind of all the applications that we write at Microsoft are working well and that our users aren't being interrupted by any issues they're causing. In addition to that, I'm also working on a Software 2.0 project. And that's kind of an interesting story how that got started. Basically, one day I was in Dallas, Texas, where I'm originally from. And my dad and I were having this talk about this new kind of neural network thing called a generative adversarial network. And those are really interesting, and I'll mention those a little bit later. But I was talking about, wouldn't it be cool? For any of you who have been to Moab, Utah, there's this really awesome national park called Arches National Park. And it's just beautiful. There's canyons, there's like these arches, there's all kinds of crazy interesting geographical features. And I thought it'd be really cool if we could somehow emulate that in software. So basically build a procedural generator that could create these arches and these canyons and stuff. Because I wasn't familiar, still not familiar with any procedural algorithms that can generate that kind of interesting terrain. So anyway, last summer, Microsoft puts on a big hackathon called 1 Week, and it's actually every year we break the record for the world's largest hackathon by participants. So last year we had about 30,000 people working on hackathon projects. Anyway, so I decided that I would build this Moab, Utah terrain generating thing. And while the outcome wasn't necessarily as successful as that might have led up to be, it did lead to kind of me joining this project which is now being owned by Microsoft Research in conjunction with the Minecraft gaming studios. So our plan is to try to use deep learning to learn to create terrain maps for video games. So for me, I'm tremendously excited about this new potential. So what exactly does Software 2.0 look like? Well, sometimes you might hear in the media that it sounds like this. But just to quote Andrew Ng, who's kind of an expert in the field, worrying about evil killer AI robots is just a little bit like worrying about overpopulation on the planet Mars. It's not to say that it isn't a problem or won't become a problem, but it's a little bit so far off in the future that maybe we need to tone down some of the investment and research that's going into trying to combat this problem, because it's not really that much of a problem just yet. So I think that what Software 2.0 is going to look like is something more like this. And this is Amazon Go, for those of you who may not have heard of it. And it's essentially a new project by Amazon where you walk into a grocery store, you just grab all the items right off the shelf and then walk out. There's no cashiers, there's no checkout lines, and the idea is that it's going to save you time and money by kind of eliminating the logistics of the checkout line process. And this is not science fiction. Any of you can go down to the Amazon Doppler building in South Lake Union district of Seattle. And I think it's open even maybe right now, maybe not because of the weather, but you just need an Amazon account and you can go there today. So I want to talk just briefly about some of the recent achievements in machine learning and AI. In the top left here, this is Google DeepMind's AlphaGo. And this is the version of the AlphaGo program which defeated 18-time World Korean Go player champion Lee Sedol. I think it's 18-time. Essentially, this is the first time that a computer program ever beat a human that was the highest rank in Go, which is 9 Dan at Go. So it was a pretty breakthrough achievement. In a similar fashion, this is OpenAI 5 playing against five professional Dota 2 players. And I believe they won like 4 out of 5 matches. And that was a huge achievement because Dota is a very kind of complex, messy, free-form nature type of game. Where Go, you really just have discrete states. So the problem is not easier, but certainly there's a smaller action space. And then on the bottom left here, you see all of these faces are fake. None of these people exist. None of these people will ever exist. This is using a neural network called a generative adversarial network. And it's able to synthesize highly photorealistic imagery of really any kind of distribution of images you can think of. This is the type of technology that my team is using to try to synthesize terrain maps in video games. And then lastly, we have, I'm sure most of you are familiar with, this is the self-driving autopilot program at Tesla. And they're using mostly just cameras. So it's mostly just imagery. They're trying to minimize the number of special sensory they use. And they're just trying to use computer vision to be able to map out their entire environment and have a car that can drive itself. And these examples really only represent kind of the tip of the iceberg for what we're going to see probably in the next decade. So as I mentioned before, Software 2.0, Karpathy identified the term. The name itself is not that important, and who knows if this is what we're going to be calling this trend moving forward. But the really important thing here to understand is that it's changing the way that we build software. But to really understand that, I think we need to kind of look at how we build software today first. So the way that we build software today is we take this really big, complex problem and we decompose it into subproblems. Some of these subproblems can then be further subdivided until the hope is that we have kind of these easier to manage base problems that we can solve, and then we somehow sum up all of these base problems back to the top to where we sort of have a solution to our original problem. So this type of explicitly telling the computer how to solve a problem is the kind of class we'll call Software 1.0. And Software 1.0 is the technology stack that we've all become used to. It's our Java programming language, it's our IDEs, it's our compilers, it's all the tools that have been created to make us very, very productive about building software. But the key is that we tell the computer exactly what to do. We tell it exactly how to solve the problem. And there's some problems that Software 1.0 is great at solving. Things that are very well defined, like protocols. My example up here, TCP IP stack, GPU shading, compilers. All of these problem domains are very kind of like well understood, or at least they have very clear requirements. So these are things that Software 1.0 really excels at. So Software 2.0 doesn't suddenly come in here and say, all of this stuff is obsolete. It just kind of puts some of the missing pieces that we've had, we desired to solve kind of on the side. So let's look at a task that is really hard for software 1.0 to solve. Consider this problem of image recognition of a cat. How do we go about solving this problem of identifying if an image contains a cat or not? Well, the first thing we can try is to simplify the problem. In this image, there's a lot of complex colors. There's a white cat and kind of yellow eyes. In general, if we want to identify a cat, maybe the color isn't so important. We could apply first a pre-processing filter on it, like a subtle edge detection, which could make the problem a little bit easier to solve. And as I mentioned before, the way that we approach problem solving in software 1.0 is that we decompose a bigger problem into subproblems. So you can think of the problem of solving whether an image is a cat or not as kind of first identifying if you have an ear and if you have a face. And the face can be subdivided into the problems. Does it have eyeballs? Does it have a nose? Does it have whiskers? And then we can just kind of put logic around it that says if all these things exist, then we have a cat. But we need to remember, what does a computer see when it has this image? All the computer really knows is a big matrix of pixel values. So how do we really write the logic that identifies if there's an ear, a nose, or whisker? I mean, do we look at neighboring pixel values and say if they're within this range of red values, within this range of green values or something, that we suddenly have an ear? It certainly seems that hard coding all these rules is going to be very hard to scale. But imagine we did it, and imagine we're able to identify if this particular image is a cat. Does anyone think that it'll work on this image? Probably not. We didn't mention anything about a tail. We didn't say anything about paws. The face is now at a completely different angle. It's highly likely that this is not going to work. So does that mean that the problem of image recognition is unsolvable? Well, the answer is no. This problem is actually easily solved with what is known as a convolutional neural network. And you can intuitively think of a convolutional neural network as this kind of layering thing where these early layers are able to identify kind of localized patterns like curvature. So the layers here would just say, oh, there's a kind of a curve here, or maybe there's a sharp edge here. And then the next layer is going to kind of take into account all of these different localized features and build up a more complex pattern. And you continue this process until you're able to identify fairly complex objects at the end. And this has worked great for these kinds of image recognition problems. In computer vision in particular, we kind of see this growing trend where every time we increase the data sets available and we have more compute power, we find a fundamentally different way about approaching computer vision. In the early days, where we may have had a single image or maybe a very small number of images, doing what we would have done with a cat is perfectly fine. You just hard code all the rules. I mean, if there's only a single image, it's going to be pretty easy. But as the number of images and the data sets have gotten bigger, with the advent of just the digital revolution, we've pushed more and more of the feature extraction to the computer. In the 90s, kind of early 2000s, we might have hard-coded some of the features like the ear and the whiskers. But then we added some statistical inference that could kind of say how much of those things matter. And then recently, as I mentioned, we have convolutional neural networks. And you can kind of think of this line as kind of the transition from 1.0 to 2.0. Here, the ConvNet completely learns all the features. There's no need to mention anything about noses, ears, or whiskers. But the programmer is still responsible for just saying how many layers we have, how deep is this network, and kind of the architecture of the network. Whereas in the future, we hope that we're going to generate all of that, and all of that will be learned as well. So the hope is that this new era of kind of computer vision will project us into the future and make things like self-driving car possible. So you've heard me mention this word neural network probably several times now. And if you're not familiar with it, it's just a data structure that's actually composed of some very simple components. In this lower left, this is called a perceptron. And it's just an operator which takes a weighted sum of its inputs, passes it through what we call a nonlinear activation function, which sounds super scary until I tell you that the most common version of a activation function is called ReLU, which is the function that takes the max of 0 or the input. So this stuff is extremely simple once you can kind of get past all of the language and kind of the wording of things. On their own, perceptrons are not all that useful. It's not until we string them together in this series of networks where they start to learn interesting behaviors. And you might hear the term deep neural network, and all that really means is that we have just a few layers. I mean, we have a deep set of layers. I mean, it's not really well defined. But the point is, back in the day when these neural networks were first invented, which I think was actually the 1940s, they certainly didn't have the computational power to kind of make use of these things and string them together. But with the, how fast GPUs and how much processing capability we have today, we've been able to scale up these networks into just these gigantic webs that are able to really learn complex behaviors. So let's take a look at this learning process. I want you to just imagine this red line as your problem or the program you're trying to create. And these blue dots represent your data points. And in this example, it doesn't really matter what these mean. You can think of this x-axis as maybe the square feet of a home. And you're trying to predict what you should price your house at, given the square feet of your home. So that follows this kind of upward trend. And what we would like to do is to parameterize a linear function, which is y equals mx plus b from math class. We want to find an m and a b that fits this blue data set as best as possible. And over here, this red dot actually is just a different way to think about the same red line, except this is how much error the output of our red line is with respect to our data points. And what our goal is to get this red point down here. Because if this is a curve that represents our error function, then we want to minimize the error with respect to this red line to its data points. So how do we do that? Well, the way that it works is that we compute what's called a gradient, which is a direction on this error curve that points towards some kind of minimum. And if we can calculate this thing, then we can update our m and our b such that this red point descends down this error curve. And we can see that simultaneously as this is happening, our actual function is getting closer and closer and closer to modeling our real data distribution. And while this is a toy example that has been known to statistics for decades, the reason why neural networks kind of take this and put it on to crack, if you want, is that we take, instead of a single variable x and two parameters m and b, our neural network can have thousands of variables and potentially millions of parameters. And this allows us to learn very, very complex behaviors and work on very complex data sets such as imagery. So what can we conclude from this process? Well, the conclusion, or at least the argument that I want to make to you, is that software 1.0, you can think of the space of all possible programs. And anything that you write in software 1.0 is kind of constrained to something that just makes intuitive sense to you as a human being, which means you're very restricted to basically just a single point on this program space. And maybe you have this point here, and maybe I make this point here. But in software 2.0, you're using optimization to search around program space. That is, you're updating all of these different parameters to your neural network that are essentially a different program until you find one that is pretty good at solving the problem that you cared about. So this really highlights this fundamental shift in the way that we go about solving programs. And this process, I'm going to try to prove it to you. It becomes very apparent when you look at agents trained to play video games, especially old Atari games. So this is a game called Qbert. Has anyone watched Wreck-It Ralph? You know, when they're breaking out of the video game, there's that little orange thing with a snout. That's Qbert. Anyway, your job as a player is to control Qbert to jump on these colored cubes, on the top of these colored cubes, and change their color. So every time you jump on the top, it changes its color. And you want to change every single cube in this pyramid to be the same color. But to do that, you have to avoid obstacles and not die. And I think you can fall off as well. So how would we write a bot or a computer program to play Qbert? Well, we might use something like the A-star pathing algorithm, and we might say for every step that Qbert is at, or current state, we'll find a cube somewhere that hasn't yet been populated by us, or the color hasn't been changed, and we'll compute a path that takes into account these enemies. Maybe that's some really high weight in your path, and he'll find even possibly the shortest path to find the cube of choice, and then it'll pick the next cube until it's descended and found everything. So this sounds like a pretty optimal way to play Qbert. But let's see how a reinforcement learning agent called Canonical ES decided the best way to play Qbert was. So far, everything looks pretty standard. Nothing is out of the ordinary. Just playing Qbert. See, he jumps. Oh. So what you're witnessing is this reinforcement learning agent found a bug in the game code of Qbert. It's found this sequence of dance moves that when done in the exact order just continues to make the scoreboard go up and up and up and up. So apparently this is the best way to play Qbert. And the point I want to make here is that this makes no intuitive sense to a human, right? It's unlikely that any of us would have found this bug. I mean, Qbert's been around for the greater part of 35 years, and to my knowledge, nobody's ever found this bug. And while this might sound like a corner case, this is true of many programs that we write in the Software 2.0 world. They seem to just find a good approximation or a good strategy for achieving our goal, and how it does that may not make any sense to you and I. To quote the professional Chinese Go player Kuji on his experience playing against DeepMind's AlphaGo Master AI, he says, "After humanity spent thousands of years improving our tactics, computers tell us that humans are completely wrong. I would go as far to say that not a single human has touched the edge of truth of Go." To me, that's pretty powerful. Just to recap, Software 1.0, we explicitly engineer systems. Software 2.0, we're finding programs by using optimization, which you can think of as directed search using training data as the guide. So does this mean that Software 2.0 is the ultimate silver bullet? Well, not exactly. For one thing, building these things is very time-consuming and laborious. Google DeepMind was able to achieve what it did by using hundreds of thousands of what they call tensor processing units in the cloud. And they trained this system to play against itself for what was 7 weeks on this massively distributed cloud system, which is the equivalent of 1,000 years of gameplay. That's certainly not practical for everybody to do for development. And the other problem is that building these systems is a little like a scientific experiment. We kind of set up our experiment. We kind of wait for a second to see what happens. We check the results. Did it solve our problem? And if the answer is no, we repeat that whole process again. And there's a lot of kind of unproductive waiting around in between these training sessions. And there's some other limitations that I'll get to in a bit. So you can think of this, again, as we're building programs from data. So if we're building programs from data, then what is the software developer's job in the Software 2.0 world? For one thing, you need to find the data that's going to somehow describe your problem, and you're going to need to find the data that somehow describes the solution. And this is not an easy task. For my project with the Minecraft team and Microsoft Research, trying to find a data set that represented exactly the type of terrain that we wanted to generate was very, very hard. And we came up with all kinds of just weird and what we thought were clever techniques, and even things like machine learning on machine learning to try to gather our data sets. So it's definitely not an easy problem. The other thing to mention is, since you're learning from your data, garbage in, you're going to get garbage out. So if you're not careful to find data that generalizes, then you're just going to learn on some specific data or noisy data, and it's not going to learn anything. Also to mention, you might hear something about neural networks being biased, but neural networks themselves have no ability to be biased. The neural network is just an objective computation of these perceptrons. What is biased, or could be biased, is the data that you presented the neural network, the data that you trained on. So essentially it learned on whatever your data set is, you need to make sure that at least it represents what you actually want it to represent, because it's going to behave exactly the way that you gave the data. So that's part of your job as a programmer in this space. But you spend probably around 80% of your time just gathering data. That's what this world looks like. So when it comes to machine learning, or when it comes to software 1.0, I should say, we've become pretty productive. But what do the tools in software 2.0 look like in that stack? Well, it doesn't really exist, unfortunately. In software 1.0, we have these things called IDEs, which package our text editor, our compiler, our debugger, our deployment tools. Everything in one nice little box with a bow on it that we can use to be very, very quick about building programs. In software 2.0, such a thing doesn't really exist. What we have are a bunch of disjoint frameworks like Google's TensorFlow, Facebook's PyTorch, Microsoft's CNTK, and we even have some higher level APIs like Keras. But we have nothing that's really a complete story. And also, we don't have very good debugging tools either. So we need something better. I hear a lot of criticism about neural networks because they seem to be this black box. We've trained this function that maps some inputs to some outputs, but we have no idea how it works or why it works. But I want to make an analogy to you that kind of says that that doesn't have to be the case. I want you, first, can we all agree that trying to understand someone else's code is a lot harder than trying to read our own code? Yeah. Right. So that's hard. And in software 2.0, it's kind of that on steroids, right? Not only did you not write the code, but no human wrote the code. The optimization wrote the code. And to put the cherry on top, you're looking at this code at the assembly level. You're just looking at the lowest level instruction set of code you didn't write. And debugging this is going to be extraordinarily difficult. So I propose something better. When we debug programs, it's not very often that we sit there and sift through the machine code anymore. Typically, we map these instructions back to our high-level source code using symbols. So why can't we do the same thing with software 2.0? Why can't we have programming languages which are higher level and have a higher abstraction meaning to humans that compile down into the lower level neural network? And then when we want to debug them, we map the weights and biases and activations back to our higher level languages, and we might be able to understand what they're doing a whole lot better. So this is a tool called GannLab, which is an attempt to try to understand what the heck is going on during the learning process. And while itself is more of a toy rather than a real tool, I think it gives us an interesting glimpse to the kind of programming tool set of the future. As I said before, that training these networks is kind of like a science experiment. There's all this wasted time in between things. What if we could watch the training process happen live and potentially even influence it before it starts going down kind of a junky path. That way we don't have to spend so much time resetting up our experiment and letting this thing run. And we can also maybe try to at least build some kind of intuition about what it learned at the end of the day. And this will be very important when we try to prevent kind of catastrophic failures. And what are these catastrophic failures, you might ask? So there is I think the most cited convolutional neural network is called AlexNet. I think it has like 30,000 citations in academic literature. So it's a very well-known image classification network. And it's able to recognize this image on the left as a bus, which is good. But what do you think happens when we take all of the pixel values of this bus and sum them with this, what seemingly looks like noisy image? What do we get? Well, we get another bus. So you would think, or you would infer, that AlexNet would also recognize this as a bus. Is that a safe assumption to make? Well, you're right. AlexNet identifies this as an ostrich. And to top it off, it's 99.7% sure of it. So what happened here? Well, this noisy image is not noise. This is a carefully crafted image that was designed to trick AlexNet. The researchers were able to look at the network and take the already trained image classifier and retrain it. But this time not to minimize an error function, but to maximize an error on a particular desired training example. So they wanted to find how they could change the input such that it would just maximize the ostrich label. And so they could then subtract that image from the bus, and then they found this noise pattern. So to define an adversarial example, it's an image that has been augmented with imperceptible non-random perturbations that arbitrarily change the network's prediction. So the question that you might ask next is, what is the minimum number of pixels that need to be changed in an image to flip its label from one class to a desired class? Can anybody guess? Do you think the minimum number of pixels is? It's 1. Or at least it's been shown in some examples to be just 1. So these are all examples of where researchers have, it's a Japanese university, Kyushu University. They devised this algorithm that can find a particular pixel to change it to a particular color that flips a class from, in this example, from ship to car with almost 100% certainty, and this image of a horse to an image, or to a label of a frog with basically absolute certainty. So this is a real problem. And you can imagine if we have these self-driving cars, like say Waymo or the Google self-driving car project, and it's driving along the street, and this team of criminals has discovered that there's this particular pattern of colors, and they go in their stencils and their X-Acto knife, and they take these little cellophane strips and stick them on a stop sign. As a human in a self-driving car, you don't really pay attention. You may not even be able to perceive those cellophane pixels. But suddenly your self-driving car is sure that what it's seeing is not a stop sign, but it's a green light or it's an empty intersection. This is bad. So this is an open area of concern, and it's kind of a strange property of neural networks. Again, they don't learn intuitive things to humans. They just simply learn some kind of high-dimensional mapping from some input to output. So we need to make sure that these things are safe for human use before we deploy them in the wild. So let's look at some of the economic opportunities. So there was this team of grad students at Stanford who decided one day that they wanted to go out into some fields and take pictures of plants. They took their cell phones and they walked around and they took the images of the tops of cabbages and lettuce and also weeds. And their goal here was to build an image recognizer that could identify given a picture of a crop, where the weeds were and what the real plants were. And then they turned this into a real product. They built this kind of, I'll go to the next slide. They built this kind of tractor combine add-on, which has these like actuators that spray herbicides. So rather than do what farmers do today, which is blanket everything in herbicides and then make sure that their plants have been genetically modified to be immune to the herbicides. This is a big problem because A, we're using a lot of herbicide, which means that our weeds, the weeds that do survive, are the ones that tend to be more likely to be immune to the herbicide. So they start to artificially evolve to be very immune to herbicide. And that means that we have to use even more because now they're slightly immune to it. But with this system, since they're able to precisely identify what a weed is, they can deploy the herbicide just to the weed. And they can avoid spraying all of their crops with the herbicide. So this is shown to have a 90% reduction in the amount of herbicide the farmers needed. And then they sold this company to John Deere for $300 million. So finally, I just wanted to end with some closing statements. For one, the 2.0 and Software 2.0 isn't meant to indicate that it's the new way to write software. And that 1.0 is this obsolete version of software development. It's not true. We don't suddenly render this decades-long investment in software development suddenly out the door. It's just that we want to distinguish it because it's a fundamentally different approach to finding solutions to problems. The other thing to note is that Software 1.0 and 2.0 are completely compatible. And they both have their trade-offs. And it's really just up to engineers in the field to decide when to deploy one strategy versus another. You just have another tool in your toolbox. And lastly, you've all heard the old saying, practice makes perfect. But this implies that we can't do any better. What if our definition of perfect is just one of many? So instead, I like to say, practice makes for a pretty good local minimum. Thank you. Yeah, I guess I'll answer anyone's questions. You have a mic, or we're just gonna raise hands, or let them yell? Let them yell. Okay, great.
For the canyons that you're trying to make for your work for like Minecraft and stuff,
yeah.
What type of data sets are you looking at? Are you taking like 3D models or like pictures of canyons themselves and try to copy it?
Yeah. So the very first thing we tried, because we wanted actually, if you're familiar with a procedural generation algorithm called Perlin noise, it's only capable of producing 2D height maps. And that's a problem because it means you could never describe something like an arc because you're only ever going to have one height value for any kind of X, Y location on a grid. So you can't have kind of these things that have multiple points. So we started actually with what's known as LiDAR in a format called LAS. And LiDAR is just point cloud data. Point cloud is just kind of a 3D volume of points in 3D space. And we trained our network on that data. The problem is those data sets are much harder to find in high resolution. So on Google Earth, they have a data set that's very, very detailed on the Arches National Park. That data set is proprietary. So we were stuck just scouring the USGS geological website. And unfortunately, we couldn't even find 3D data on Moab, Utah. So we actually switched it to White Canyon, which is also in Utah somewhere. And it had some success, but doing things in 3D was very, very, very expensive computationally. So for the project that we're working on now with Microsoft Research and Minecraft, we scaled it down just to height maps again, with the intention that eventually we scale this thing up and go back to 3D. So again, acquiring data sets is a very challenging problem. Yep.
Back to that set of slides you were showing us earlier about the school bus
looking
like an ostrich.
Yeah.
So that's the same kind of an algorithm that's going to be used, for example, in self-driving cars.
Yes, correct.
So if you're looking at the image analysis, looking at a stop sign, and there's graffiti on the sky, or the dirt, or anything at all like that, any
Yeah.
kind of alteration to what should be a pristine image. How can you have any level of certainty?
So,
algorithms coming up with the
right. So remember that the mud is kind of random, right? It's not carefully crafted. These adversarial examples are, you have to look into the network themselves to see how the weights and biases get manipulated with particular inputs. So things like mud and stuff are really not a problem for image classifiers. It's only if you deliberately try to fool them is it even possible. The second property of these things, when you move from imagery to video, it's kind of a saving grace. The likelihood that this exact pattern of noise again fools the network at a slightly different perspective goes down exponentially. So a car that's moving toward a stop sign is much less likely to be fooled by an attack like this. However, the attacks could be more advanced, and we're not sure to what extent can these properties be exploited. But certainly, when you move from stationary imagery to video, you decrease the likelihood from an attack of this nature. So that's kind of a thank goodness. And then they're also mixing non-imagery data as well. They're using, I think, sonar. There's also a sonar detector on the Teslas. So the hope is that you can kind of have redundancy between different sensor technology. So even if you were able to fool one, the likelihood that you could fool all five is much lower. So yeah, this is a known problem, and there is active research. I don't remember. I can link you a paper at the end if you want to check it out.
When I first saw this slide, when I saw that middle image there, what I thought we were looking at was the differences in the pixel reception on a CCD. Because they're different from one to the next, right? They can be different. Like if you capture an image on CCD, the pixels from one to the next, they respond slightly differently from one another, although they shouldn't. I thought that's what we were looking at first.
Oh no, we're just looking at just a
deliberate pattern that somebody came up with to fool the algorithm. Is that right?
Yes, that's correct. Yeah, and they had to have access to the network. So that's the other kind of key here. Without being able to take the already trained network that you know is deployed and re-optimizing it to maximize the error, essentially, it's not really possible. I mean, there are some attacks that do it through inference, but it's very slow. You have to, look at an output, look at an input. Without having access to the network, it's a much harder attack.
So, a couple of things. One, this particular noise, would that only work for identifying buses, or is that a bug in its image in general? This
particular noise pattern is only to fool a particular network called AlexNet on this particular example.
Okay.
Yeah, it does not generalize. Sir?
On that particular image.
Yes.
Right, so if it's a video and you're moving, that won't probably won't fool the next
With this kind of simple attack, yeah. However, if you're thinking about other technologies like facial recognition technology that may just take a single screenshot of an image and then make some decision on that, this could be a problem there. Also, we're not sure what else you can do with this, right? Like, could you build some kind of more general sequence of noise that rather than just fool one particular example to a very, very strong degree, can you find just a noise that tends to fool things in general, maybe not as strongly, but just enough to push the label from being a bus to an ostrich? So rather than have this 99% certainty, you could maybe, because again, we're using this technique that lets us search this big complex space, problem space, to find these weird inputs. It's possible that we could find something that is more general as an attack.
The other thing I'm wondering about this specific example, is that something that a programmer would be able to hack out of the system?
Yes. Without access to the network, you can do it still. But you have to basically try and input, and look at the output. So it's very slow, because you have to literally run the whole feed-forward propagation to wait for the output. But yeah, I think there is actually a paper where researchers have done that. It was on very low resolution images, so we're not sure how practical it is in the real world.
How do you go about testing all of this AI and neural networks.
Yeah.
I mean, as a tester, I'm looking at it,
Mhm.
and boy, if it's one pixel, and
Yeah.
that's a very complex.
Yeah, that's a great question. Yeah, testing this stuff is tricky. And when you find an edge case, right, and this is something that Karpathy mentions in his talk, where they may never have encountered this scenario before. The really only way to combat it is to go find data on that example and then retrain the network. But certainly, you can imagine that if you had written unit tests, if it was even possible to write unit tests for a neural network, every time you retrain it, potentially that would fail. So testing these things is hard. And you can test the general case pretty easily, right? You run images, millions of images of buses and make sure that they're all correct. And you're like, 99.9% accuracy, pass our test. But sometimes when these things fail, they fail hard. I can give you an example. There was this other image network. I think it was deployed at least as a kind of a test for a courts to analyze images of people to identify if they meet a particular description of a suspect. And the researchers took this network or the architecture and trained it on pictures of huskies and wolves to identify between the two. And they found an example of where the network identified a husky dog as a wolf. And they dug deeper, and they looked at the activations that were being lit up when it was looking at a picture of a husky. And they discovered that the reason why it said it was a wolf was not because of anything, the dog at all. It was just the snow in the image. So essentially, the network had just learned, in the presence of snow, it's a wolf. This is not desirable. So even though we're achieving these insanely good high accuracies, we have to be careful about bias, and we have to be careful about what these things are actually learning. If you have a data set where something is true 98% of the time, you can build a network that has 98% accuracy by just returning true. It's not a good model. It doesn't predict anything. So you need to look at not just the total accuracy of these things. We need to look at the recall, and we need to look at the precision. And we need to see that when we come up with false negatives, that we don't come up with really bad false negatives. So that is an absolute area of concern. And I'm not sure how to test it.
When you describe that the perceptrons are generally, fairly simple.
Yep.
Is it possible that for maybe like some applications of software, having more complex algorithms being run in each one of those be more productive than just simple?
So simple adds and additions and multiplications, yeah. I actually kind of thought about this exact thing earlier today. I was trying to think, could you build a web browser renderer just by taking inputs of HTML and looking at the output pixel buffer from Chrome? And the cool thing about this is that you have tons of training data, right? You could just literally randomly scour the internet, look at HTML pages, and look at what they rendered. And could you train a neural network page renderer? And I thought, it's going to be pretty hard when you're trying to render an image link. You have a URL. What the heck is that image going to be? I mean, what it's going to learn is going to be maybe there's some pattern in the URL name, and it would, maybe if it has some name in there, like a celebrity, it would sort of make that celebrity. But what if you had an operation in the neural network that could do a WebGet call, right? Like it could actually take the link and go download it. I think with that kind of an operator, you could actually probably build a fairly decent renderer. So that was just an idea that I had where instead of just summing weights and biases or doing adds and multiplications, could you have an operator in the network that says, at this time I'm going to go download something? So I think there is lots to be explored. We really don't know how far this stuff we can take this stuff. There's a kind of a silly paper on Archive called gradient descent by gradient descent, or it's like learning basically how to structure a network by using a neural network to learn how to structure it. So it's kind of like this recursive self-learning thing. And while it hasn't been totally successful, the principle, we could use it to find more complex network or kind of basic network types, these nodes, these perceptrons, that could maybe lead to more complex behavior. But do know that neural networks are universal function approximators. Theoretically, they're capable of mapping any input to any output. So they could technically learn to do a web page download somehow by manipulating your machine. In theory. It's not likely, but it could happen. But I think you're right. Yeah, those are areas to be explored, certainly. And we do have other operations than just the perceptron. So convolutional neural networks use node types that do kernel convolutions. If you're not familiar with that, it's just a little matrix that you pass over an image, and you apply some operation to those neighboring pixels. So, you know, in Photoshop, you have like a Gaussian blur, mean blur, and all these kind of like filter sepia and stuff. Essentially, the blur is just passing this little, called the convolutional kernel, over the image and averaging the surrounding pixel values. So that same concept is a node type in the convolutional neural network. Rather than you tell it what weights are in that kernel, like how important are certain pixels to sum for this blur, it learns those values. So there's certainly more to it than just perceptron. But in general, that's kind of the basic operator. Yeah. Any other question? I think that's a wrap. All right. Thank you.